Hello and welcome to this podcast for Electropages. I'm your host, Robin Mitchell. In today's special episode, we are joined by a Charlie Hauck from Bluespec. And the first thing I'd like to say is thank you for joining us today.
Sure. Glad to be here, Robin.
Fantastic. So the first question I'd like to ask you before we jump into all the details is, could you talk a bit about yourself, your role in the company, and the things you like to do in your free time?
Sure. I'm a electrical engineer by background. Started designing chips back in the late 80s. Was through a couple of different chip companies like Kendall Square Research, which did supercomputer chipsets, and then LSA Logic, which was the original ASIC company. And then after that, it was a company called Lextra, which was one of the first microprocessor IP companies that did a MIPS compatible microprocessor, which is very relevant to where we are today with Bluespec in our role with RISC-V IP and RISC-V tools. So what I've been at Bluespec since late 2006. Been the CEO, basically directing strategic product definitions and development. Bluespec provides both RISC-V cores as silicon IP and also tools for helping people use RISC-V cores, whether they're Bluespec cores or not, in order to develop with those cores efficiently, because RISC-V is new and there's some new things to learn and there's a lot of options. And so we provide tools that help customers sort out all of those options and then efficiently apply it to their particular application or their particular problem. In addition, we have tools that help customers not only kind of use it efficiently, but also optimize RISC-V cores efficiently. And one of the things that we'll be talking about is the big opportunity that RISC-V provides in enabling hardware acceleration, which has become a required way for achieving the performance and power requirements that are necessary in today's markets. So in summary, we provide RISC-V cores as silicon IP and RISC-V tools as EDA tools. And the company itself started out as an EDA company in 2003, in which it took to market some really advanced design tools and hardware description languages to help people design and verify their ASICs and FPGAs much more efficiently. And we use that background. We still have those tools. We pivoted away from a pure Bluespec system Verilog company in the 2014 timeframe. We were involved with RISC-V from the very start, and having had a lot of employees that were former processor developers, we made a very natural pivot from what we were doing with Bluespec system Verilog to a RISC-V centric company. We still use all of that advanced technology internally, and it helps us do better RISC-V cores and better tools. But our focus now is exclusively on RISC-V.
That's absolutely fantastic. Now, I must quickly ask you, when did you start? When did you first go into industry then?
I was first in industry in the mid 80s.
Blimey, so it was really at the time of the peak. Oh, wow, that's absolutely fantastic. I could have hours of conversation about that for sure.
Yeah, it was at Commodore Computer. It was fresh from MIT, looking to do my first chip. They threw me on a floppy disk controller replacement with Western Digital Design, and it was kind of the luck of the first job ever in having done a chip that would actually show up in Toys R Us in a product. And it was very interesting to be able to take our children at the time, we had 2, we have 4 now, and show them a disk drive in the case and say, Daddy's chip is in that box. Now, that was beginner's luck, because after that, everything got going to be more sophisticated with supercomputers and things like that. So never again was I able to point to something to my children and say, that's where our chip is. But it was good to have that first experience.
I can absolutely appreciate that. Of course, I must ask, you still have an original die of one of your chips?
We do, yes.
Good, right. I was about to say, it would have been criminal if you didn't have at least a die that you designed yourself. That'd be criminal. Yeah. But you didn't answer the most important question. What is it you like to do in your free time?
Free time, primarily read.
Read? That's fair enough. I was going to say, because you can't say electronics, because that doesn't count.
I get enough electronics during the day. Most of it's
totally
reading, history and science.
Fantastic. You sound like my kind of guy. Absolutely. None of that fiction nonsense. We're talking science. We're talking science, facts, non-fiction only. So I totally get that. So my first question to you is when it comes to, I'd say, RISC-V in general, what would you say has been the biggest challenge that it's faced since its conception around about a decade ago?
Well, it's faced several challenges. I mean, one is that the industry's tried to produce open source RISC-V ISAs. And let me just kind of give an explanation. So when I say ISA, I mean instruction set architecture.
Yeah.
And what that is the set of instructions that the particular processor implementations use. And so going way back, there was MIPS. Everybody knows about ARM now. x86 from Intel is an instruction set architecture,
Yeah.
and there are many others that came up in order to do special purpose types of things. Spark was an early one as well that attempted to become an open source instruction set architecture that others could design to. Unlike with x86, it's primarily Intel and AMD that design to that. With ARM, it's primarily ARM as a silicon IP supplier that designs to the ARM ISAs. There are special companies that take certain kinds of architectural licenses that enable them to implement their own versions of ARM processors. But the ISAs themselves have always been proprietary, and they've always been controlled by some private company. This is the first time that there was an open instruction set architecture, an ISA, that actually succeeded to the level that it has and will succeed to the level that it will. And so the early and the first challenge that they had, and when I say they, this is Krista Sonovich and Dave Patterson from Berkeley, along with a bunch of very talented and brilliant grad students. How do we come up with an instruction set architecture that's actually going to have the credibility within the industry to be accepted? Because lots of people would say these are just kind of like academic type exercises or toys. Yeah. And RISC-V did indeed start out at that. The original goal of RISC-V was to be able to have a single instruction set architecture that multiple research groups could work against so that they can compare their results on an apples-to-apples basis. And there were a lot of papers and things that weren't accepted because the results couldn't be proven because the researchers used a very specific ad hoc instruction set architecture that nobody else could really kind of repeat or confirm the results of. So what the Berkeley guys did is they decided they were going to fix this primarily for R&D. But it just so happened that Dave Patterson was one of the guys that popularized, along with Hennessy, the RISC-V, the RISC approach, reduced instruction set computing. The whole idea was, let's not make really complex computers with really complex instructions, but let's get really simple instructions that can be composed together to do things in a very efficient way. And so they started out with the first challenge was just getting academia to catch on, and it just took over academia very quickly because the 5 part in RISC-V is basically the 5th generation. Yeah. And what I think it was Patterson has said is, listen, we took everything that we learned since the mid 80s, around or even earlier for RISC type architectural development. We've retained all the good things and we've eliminated all the bad things. And in addition to that, they also put together an instruction set architecture that was developed for today's challenges, primarily things like virtualization, where you can use processors and reallocate hardware resources without actually having to physically move resources around, and acceleration, which they saw, with Moore's law. We could talk about particularly what that means, quote unquote, coming to an end. With that happening, what do we need to do now to meet the future challenges of performance and power that we can't just get by jumping to a new process mode and going faster and going with lower power? And so they architected this to be able to extend it to work well with hardware acceleration, and we can talk a little bit about domain-specific processors and things like that. So with all of that, that really got them to establish their presence and take over what was at the time academic R&D. The next step was there were a bunch of forward-looking private companies. Western Digital was one that basically said, you know what? This instruction set architecture, like all others, has the pedigree like we haven't seen before. It's very well architected. We've got a lot of cases where we need to innovate, And we can't because other people, private companies, are controlling the pace of innovation. They're controlling what to do. And a company like Western Digital needed to do some very specific things for disk drive management, and all they wanted to be able to do was to be able to innovate on their own terms. And so they looked at the RISC-V processors. They very quickly kind of came up to speed on that, along with a bunch of other companies. And the original RISC-V Foundation was then formed in order to bring up the use and the promotion of the RISC-V ISA in industry. So that was the second big challenge. And you can imagine at the time people were saying, well, this hasn't worked before, and open instruction set architectures, they're not going to fly. But what they hadn't bet on was that this was maybe the third or fourth try of an open instruction set architecture, and these were the guys that if anybody can do it, these were the guys that were going to do it, and it started to take hold in certain kind of like very forward looking companies in industry, and so that was the next big challenge, which was how do we make the jump from academia into industry, and that went pretty easily. And I should say easily, but it went in a pretty straightforward manner. But then the next thing was, and there are lots of different other kinds of challenges that came up. But the ones that I remember being a part of, the first one of the founding companies for the RISC-V Foundation, back in the first years, was lots of talks about, well, RISC-V has got all of this kind of like openness and flexibility. How do we keep fragmentation from happening? We've got and the other big thing that happened is like lots of other, not only companies, but countries and regions that had been previously shut out of doing processor development because there were proprietary ISAs that were the only ones that were available. All of these other regions and countries were interested in using RISC-V to promote their own brand of RISC-V. So there was a very big concern about fragmentation, and that RISC-V processors would be built in different parts of the world that can't talk to each other. And that was something that the RISC-V Foundation, and to very much because of people like Krista and Dave Patterson, and then Mark Himmelstein, as you mentioned, those were the people, along with lots of others, in the board of directors and everybody else in the task groups. The really hard problem that was focused on, the big challenge was to eliminate the possibility of fragmentation. And I think that's largely, that's always a challenge. You always have to be vigilant against that. But that's largely a past challenge that they've overcome. And then
I think a lot of the challenges that you're talking about, they do remind me a lot of that sort of mid '80s period where you had the IBM standards coming out, you had the ISA, actually the ISA buses coming out, and you had that really big issue of, well, we've got a computer architecture in terms of how all the components connect together, but if the BIOS itself is completely closed and no one else can make the computers except for us, so it sounds like that the problems that it's faced are almost identical to those of the machines in the past.
They are, and as you mentioned, like the equivalent of the let's say the buses and things like that. There's the instruction set architecture, which the instructions that a processor runs. But in addition to that, there's a platform specification, and a platform describes all of the other pieces of the hardware subsystem and the firmware that runs on top of that, so that there is a clear contract between the hardware developers and the software developers, so that what the current challenge is the software ecosystem. How well and how good is the software ecosystem going to be developed? And that was one of the things that they said from the very beginning, is that everything else that failed before typically fails. And any type of processor doesn't fail because the hardware is typically bad or insufficient in some way. It fails because the attempt to get the software ecosystem going and the momentum behind that never took off, because there weren't enough of people that showed enough of confidence in that architecture from the beginning to be able to invest in the ecosystem. And there are lots of companies that do operating systems and that do tool chains. Is they look at there have been lots of different processors that have come up over the decades, and they look at each of these and say, well, how do we know that it makes sense to invest a lot of our time and effort, support our tools and our operating systems and our firmware and libraries to this architecture, because it may go nowhere. And so we're beyond that point now, where there's a robust and growing RISC-V ecosystem, primarily defined by the software that will run on it, which is the all-important success factor for a processor.
And I think it would be also fair as well to say that one driving force that's really helped a lot is ironically the not to get too political, but the situation with China, where it's been locked out of a lot of key technologies, as well as India, like you said, as you talk about regions being locked out of proprietary technologies. Suddenly, RISC-V has landed on their door. Like the US is like, oh, we don't want them to have that technology, but there's nothing they can do because it's open source.
Yep.
So it gives them the freedom to do it, and it's kind of a double-edged sword, because while they're now getting access to newer and newer technologies, it also means it's actually helped it grow even more. So everyone kind of benefits from that at the same time.
Yeah, I mean it's basically the foundation under which everybody competes. And if you believe that any given country can compete, given a level playing field, then it's good for everybody. If you raise the playing field, is good for everyone. Doesn't necessarily mean that the people that want to compete and feel that they compete and have an edge can't do it. They just need to concentrate on different things. You don't concentrate on the basics of a processor anymore. You concentrate on all the things you build on top of a processor.
Because one thing I've noticed about RISC-V design is that in the West, I tend to see RISC-V being integrated almost silently into products, so you don't really tend to see its influence.
Right. Yeah.
But what I've seen from China, especially, I've seen really cheap, really small microcontrollers coming out, which are just RISC-V microcontrollers, and I quite like that because it allows people, engineers who are sort of trained, they can get to work with RISC-V quicker. So, I think it's nice to see that balance of, we've got high-end technologies, like you say, Western digital drives. They're integrating RISC-V. You don't really notice it, but it's helping it, move forward in a very professional capacity. And on the other side, you've got other countries who are making extremely tiny, extremely cheap microcontrollers that allow people to at least experiment with the architecture without having to try and find an FPGA to simulate that core.
Right.
But I think the conversation definitely needs to move towards accelerators, because you mentioned earlier about RISC machines being reduced instruction sets compared to the complex instruction sets of x86 and x64. Right. And one thing I've always noticed is that with RISC-V, you have like maybe 30 or 40 instructions. I'm not quite sure how many instructions there are, but I know it's a lot less than a typical Intel processor. But in terms of accelerators and more so, how is that seeing challenges, the reduced instruction set for modern computing applications like AI, machine learning, and maybe things like advanced programs, essentially?
Yeah. So the first thing is just there's always this tension between generality and specific implementation. And one of the things that we're lucky is that if you look at even the most efficient processors, the RISC-V, RISC processors, and in particular RISC-V processors. And just to give you an example, I think, I've seen the numbers, and maybe I don't have the numbers correct, but I think maybe the RISC-V ISA spec is maybe 200 pages or something, and the ARM spec is like 3,500 pages. I mean, it's a big difference.
Oh, blimey.
Not to say that and ARM, to be fair, ARM started in the 90s, and because of backwards compatibility with software, as they move forward and believe me, ARM is like, it's the top of the mountain in terms of, their ecosystem and their cores and things like that. So, but what they needed to do over the years was they needed to make sure that things were somewhat backwards compatible because of all the legacy software and things that needed to still work, based on products that their customers were building using their cores that couldn't move as fast as maybe the cores could. Or as maybe
I would like to interject very quickly about that backwards compatibility. It does infuriate me as an engineer that a modern x64 processor is still technically compatible with software from the mid-80s running 16-bit applications. And like you say, because they have to maintain that backward compatibility, you make it complex. You've got wasted silicon space. It becomes less efficient. And whereas with something like RISC-V, because it's brand new, it can be designed with modern applications in mind.
Right. And so that shows up in bloat, right? In the bloat in the ISA, and that means things are a lot less efficient because you have to maintain that bloat. And what so when you look at RISC-V, you do some comparisons of processor implementations that from an architectural point of view are the same level of power, which is, the amount of work that happens per instruction on average, to, let's say, an ARM processor. The RISC-V processors are much smaller and much more power efficient, for the same overall performance at both frequency and architectural performance. And so the interesting thing is that when you look at, no matter what processor used, in order to get general purpose execution, and software is great, right? They talk about software is eating the world, and what that kind of means that is something can be done in software, it should be done in software. And only when you run up against either the performance or the power limitations of software should you actually try to go off and do hardware, because software is so much easier to write, it's so much easier to debug, it's so much easier to test, it's so much easier to modify, and software is a big part of the productivity in this world. But the cost of doing that, the cost of the generality of being able to take any, lots of different kind of software applications and just doing a mechanical compilation onto a single piece of hardware, that generality has overhead. And that overhead can be anywhere from, 10x to a couple of 1000x, depending upon how sophisticated the processor is. So to give you an example, so a very low end processor, there might be like a 10x difference. That means that the overhead of taking an instruction and implementing it and bringing all of the operands in. If you want to add two numbers, for instance, if you want to bring the operand in and add those two instructions, there's all of this overhead. You have to decode the instruction. You have to figure out where the operands are. You have to go out to memory and pull them in. And finally, you get down to the really small point in the middle of all of this where there's the little adder. And that little adder just does it in a flash, right? It does it with, very little area and very little power. But to set that instruction up took another 9 times as much implementation and energy to do that, right? Now if you get into very sophisticated processors that are superscalar, that is, they execute more than one instruction at a time, and they've got all kinds of out of order processing, and they do all these ways to try to make instruction execution be as parallel and as as powerful as possible. They can be 99% overhead to get that little add instruction to work. And so that's in some ways that's the good news. The good news is for what we've come to really accept in terms of software implementations on these big powerful processors, and it does some amazing things. There's 99% overhead in that, so that if you wanted to take one particular application, let's say a machine learning inference function or algorithm, and you wanted to put that in specific hardware that is customized just to do that function, you can be anywhere from 10 times to 150,000 times faster. And you can be anywhere from 10 times to tens of thousands of times less power, and that's what hardware acceleration is all about. It's about how do we take things that are costing us a lot of time and effort in software that a general purpose piece of hardware can't do well, and how do we move those out into specific hardware to do that very efficiently. So there's two things that we're very lucky to have on our side. One is that there's this basic inefficiency of being able to of having to do general purpose type software execution. So, and there's ways for us to eliminate that inefficiency. And then the other thing is, if you look at many software applications, it's not like every part of the software uses the same amount of compute resources and powers. If you do an audit of where all the computation and all the energy is going, you'll see big spikes. So in the case of machine learning, you'll see big spikes in things like, matrix multiplications and things like that. So what we can do is we can leverage the fact that there are big spikes and move the code that in which those big spikes happen, move that into a specific piece of hardware that is connected to the processor in some efficient way, and thereby speed up the overall application.
And I think it'd also be fair to say as well, with that large spike, that can also be a bottleneck as well. So you'll find that 95% of the time, you're not actually fully utilizing your resources, but there's only one point in time where they're being pushed too far. So if you can shift, as you say, if you can shift that from software to hardware, suddenly everything else can also scale up as well in terms of system utilization.
Right. Yeah. I mean, we got an example now, a very simple example. where somebody's doing some type of signal processing for a GPS application, and there's a lot of signal processing, and that signal processing represents over 90% of what the job is. And so if you move that out into accelerators, and we have tools for helping people do that, you can take what otherwise was, a stressing your current, even high-end ARM implementation. You can take that out, put that into an accelerator, which has a RISC-V front end, and we'll talk about that earlier, because a big part of using hardware is to start to add as much hardware as much software as possible into the hardware implementation in a way that it reduces all the complexity of doing hardware. So the goal here is to try to put things into hardware that give you the performance and power increases without taking the penalty of hardware productivity, which is anywhere from 10 to 50 times less productive than developing software, right? And that's what hardware acceleration is about, which is identify where those hotspots are, efficiently and carefully move those into hardware, and then have a good communication path between the processors and the accelerators, so that you don't give back a lot of the benefit that you got from the hardware.
And so would you say that this ability to program or to dictate functions purely in software is why engineers are kind of going more towards those little RISC-V cores as opposed to a dedicated FPGA or ASIC?
Well, I mean, everybody, no matter what kind of core it is going to software if they can, because time to market and just the benefits of that are just tremendous, right? I mean, all the productivity we've seen over the last couple of decades has been because of software. Because
absolutely,
and if you look at like where processors are, I mean, the processors are doing amazing things. It's very difficult sometimes to beat a processor at doing some particular implementation, and that's where the challenge of hardware acceleration comes in, which is the processors have gotten so good that unless you're really at the top of your game in terms of hardware development and algorithmic expertise, you're not going to beat those processors, and that's the challenge. That's where kind of like the ASIC and FPGA development comes in. But one thing to kind of note is there's a very straightforward way of doing this, and we've been doing this all along. You take an example is like with a GPU. A GPU is a way of taking a processor architecture and doing a certain class of software much more effectively because of the microarchitecture that it uses, by basically replicating a whole bunch of data path units for doing the data path type processing, and then coming up with the right type of control, which is no small feat, to be able to program certain kinds of applications into this multiple architecture type of implementation and get it to run productively. So GPUs have, for certain applications, have extended the life, greatly of what you can do in software. But even at some point, that requires certain types of applications which are, fairly kind of regularly structured. And another good thing that comes into this is all this great capability that we're seeing with machine learning, which sometimes is really kind of like hard to understand how it does what it does, given that it's basically, when you look down into the details, it's a bunch of multiply and accumulates. Those types of implementations work well in GPUs, and that's why we see, the success of NVIDIA. We see all kinds of other companies jumping in to try to do some, alternatives to NVIDIA, because there was a particular kind of application that just happened to fit well on that architecture. But that, go ahead.
But even that, and this is, I think, what we're finding now, is that even though GPUs have proven themselves to be fantastic for neural deep learning, I think it'd be fair to say that they still carry a lot of bloat in them because they weren't originally designed for AI. So you might find that, I don't know how much in terms of what the power percentage would be, but I imagine a significant amount of power is being consumed on non-AI related functions.
They are, but what they do is they amortize that. So before, when we were talking about everything you need to do to kind of go out and to get the operands and decode the instruction and bring it in, that was for one operation. So now if a GPU takes that same amount of work, which is the same for every one of the sub-processors or data paths that are in there, if you amortize that across 128 or 256, SIMD type processors, now you've taken that overhead down and you become more competitive, right? So that works to a certain extent. If you wanted to say, okay, I've got H.264 video encoding and decoding, which is a big part of what we need to do, for, all of the video type things and any types of servers like that. If you take H.264, which is a very kind of irregular type, you got to you do a bunch of data calculations, then you make some decisions, then you decide what you're going to do next. That type of thing does not port nicely to either a processor or a GPU because there's a lot of irregularities, right? So even if you look at NVIDIA processors, they'll have, and a bunch of ARM processors, they'll have H.264 blocks, or they're sub like ASIC blocks, or they're accelerators, because that doesn't map well onto a programmable architecture. So that example is just, you just keep applying that over and over again for different types of applications that are coming up, and you can see where the hardware acceleration comes in. And so one of the things that's interesting is, an easy approach is to say, well, we've got ASICs and FPGAs, and I would say that, you could say, are ASICs and FPGAs, replacing GPUs because they do things faster, or do GPUs replace ASICs and FPGAs because they could do things much more efficiently? It's one, it's both, it's both cases, right? But what we're seeing now is, you could take, for acceleration, you could say, just take something that can be done on an ASIC, take something that can be done in a CPU, put those two things together on a die, and that's where you get a hardware acceleration. That's a very kind of simplistic way of looking at it. In some ways that works, and even in those cases, you can't do that because it's kind of very difficult. You can't take an x86 processor and build your own implementation that has an x86 and your stuff on a die, because the licensing doesn't work that way. Now, in the future, things like that might change as we get into chiplets and things like that allow you to very efficiently take something in a different kind of packaging form factor and connect it to your own ASIC. But that's not entirely here yet, but we'll eventually go there. With ARM, you can take an ARM processor, you can license the IP, and you can put your kind of like ASIC components around that and speed things up. But ARM has got like more difficult kinds of licensing type things, and it's more expensive. And so what RISC-V has done is they've opened up, just the logistics of being able to combine hardware and processors on the same die.
But I think we should also mention about ARM, which is that not only are its licensing terms difficult at the best of times, but what if it decides to change them halfway, like I think it did? I think it might have been ARM recently, or was it Qualcomm? But the moment you have a third-party IP holder, if they decide to suddenly change the nature of the game, go, actually, we're going to start charging people on a different basis, it means that all the hardware you've been building, reliant on their ecosystem, is suddenly affected by that, and it might make or break a project. But I want to quickly ask you about Bluespec and how does Bluespec fit in all of this RISC-V ongoings?
Yeah, so the way Bluespec fits in is just the very kind of basic logistics of taking something relatively new like RISC-V and putting that into your design flow, right? So if you look at RISC-V, unlike ARM and like x86, there's just one place you go to for implementations of those cores. You go to ARM. ARM's in the case of Verilog, right? So in the case of RISC-V, there are a dozen or more credible IP suppliers right now. And RISC-V itself is kind of fairly new, and the ecosystem's still developing. So people, as motivated they still need help. And there are lots of open source cores as well, which is, there's the CHIPS Alliance, there's Open Hardware Group. And while the RISC-V Foundation, which is now RISC-V International, is focused on the RISC-V spec, or the instruction set architecture and the platform specifications, these other groups are looking to extend that open source to implementations of the specification.
And now I think that's a really important point we need to make to our audience, which is that there's some general confusion sometimes where people think that RISC-V are the ones designing the processor itself, but they're not. They're just making the instruction set that the processor needs to follow. So anyone can make a RISC-V processor. They could make it out of relays, they could make it out of vacuum tubes if they wanted to. But the point is, if you give that one or a high-tech version the same instruction, they should execute it in the same way, such that they come to the same answer.
Right. So there's an explosion of options, right? And so what we're doing is we're helping customers sort through all of the options and navigate that.
Yep.
And so you gave me an example with a customer we had that said, he was a design manager. He said, my boss told me to go off and to evaluate a couple of different RISC-V cores for this project. And he said, it just like took forever. We got through one, and then when we imagined everything we had to do three more, like my boss wanted me to do, it was just too much work. And so Bluespec came in and said, listen, we looked at all of these cores, and a lot of these cores were open source, and people are more and more open to open source cores because you can actually prove that they work. And when you prove that they work, it doesn't matter kind of like where it came from. You can have the technical proof with all of the instruction set, tests and the compliance tests and everything else to say that this works. And particularly if you put them into FPGAs as either a prototype or as an end product, you can run your own software and see that your own software and the other components that you hook up work as well. So what Bluespec fits in is we help users, people that are considering or starting to use RISC-V, navigate that whole jungle of opportunities. There's a lot of benefit there. There's a lot of like free benefit in terms of open source cores, like the Open Hardware Group core, the CVA6 from Open Hardware Group, which is very popular in Europe. There's a lot of free value there as long as you know how to mine it, right? And so what Bluespec does is we help those users mine that out, and we provide them the tools that which they can safely and efficiently navigate all of the opportunities that RISC-V provides. And then the second thing that we do is one of the main motivations for people going to RISC-V is I need lower power and higher performance, and so you can do that with RISC-V. I mentioned before, besides, virtualization, one of the other major things that RISC-V was architected with in mind was hardware acceleration. And one of the very efficient ways to do hardware acceleration, as opposed to just building an ASIC block and kind of gluing it onto a processor in a die, is to look at something that's much more reusable. And so there's this idea of domain-specific processors in which you can carefully define the kinds of hardware accelerators you're going to use in such a way that they're more like functions than they are just one big kind of monolithic type implementation. In hardware is not very kind of flexible or configurable or reusable. And you can define these functions in such a way that you can put a certain amount of software orchestration around that in the processor that will allow you to use that set of accelerators for a whole set of applications in a given domain, like machine learning or like signal processing for communications or genomic processing and things like that. So that starts to hit on what the real challenge is of hardware acceleration, which is maintaining the productivity of software as much as you can while getting the benefit of performance and power from the hardware itself. And the real challenge is to figure out how do you put those two together, how do you architect your system so that you maintain productivity with the performance and power capabilities that you need. And so what RISC-V does is RISC-V allows for custom extensions to the RISC-V ISA. It's very well spelled out how you do that, how it fits into the instruction decoding, so that we won't end up producing, fragmented processor implementations.
And I think that's one of my biggest concerns when I see people developing their own sort of like extensions to it, because I get a little bit like, well, isn't the whole point we're supposed to be following the same standard? But like you say, that may not be possible anyway, because RISC-V can only go so far. There are going to be times where you need to have application-specific instructions that help to accelerate something very, very specific. And if you haven't got that ability, then you'll probably find that RISC-V might have not done as well as it has had it basically not allowed that, essentially. So in other words, if RISC-V didn't allow for those extensions, it may have not been as successful as it has been today.
Well, that's true. I think it's a lot of what people are looking to innovate, right? And this is an opportunity to innovate. If you take an ARM core, you can't add your own custom instructions, and there's a big benefit to that. I mean, you can look at, there are some instructions like in genomics, for instance, which take on the order RISC, reduced instructions. So these are very simple instructions to do a complex function like alignment or something inside a genomics type of implementation. There can easily be like 150 to 200 instructions to do one very simple thing, and one very simple iteration that happens over and over again, millions of times. So that is something that if you put into a complex instruction, that can happen in a single cycle. And so you get this speed up of hundreds of times. And that's okay to do. So look at this. That custom instruction can be just that up in libraries that supplier of any specific provides, that users worry about whether a compiler actually uses those instructions. There are ways that those custom instructions so that they very efficiently, but you don't necessarily expose that might cause segmentation, right?
Okay.
So that's the key of why you can do without fragmentation. Now there are some cases somebody, I'm doing some security or something, I'm actually going to have a version of a compiler that will recognize these instructions. So if that domain processors, and it's okay to have a compiler and ship the compiler with that. So there's a case where if you have a library, you can that library. If you don't. All the tool chains are compatibly.
Oh, and then it's like it's almost the so you have like a core for the RISC-V, and then if you have like inside there, I have like a decision tree. If you haven't got this, use this version that's slow, and it will still transfer essentially. Right.
And we already do that now. I mean, we do that with it's been with processors forever. But you can compile code for a RISC-V processor that has an integer multiplier and compressed instruction set, but not floating point. And then you just say, it's like dash, IMAC, right? Or you can do dash GC, where G says, I have added F and D extensions, which are the single precision and double precision floating point. And so that all works out. And so what RISC-V International did is they made sure they spec this in a way that you could have your cake and eat it too when it came to custom instructions and not cause fragmentation. And then the other thing that happens is when there are lots of parts of the opcode space that are reserved, so that when enough people say we really want a set of custom instructions for bit manipulation or cryptography, RISC-V International says, okay, we're going to address that. We're going to put a task group together. We're going to define an extension. We're going to run that through a bunch of tests to make sure that we actually validate that this is going to do what it's going to do, and then we get it approved by the RISC-V International board of directors, and we provide that to everybody. So I would say 90% or more of the need for custom extensions is going to be handled by RISC-V International in a very non-fragmented, very specific way in which everybody kind of gets what they want without all of the chaos that might come with it. And then you've got there's an escape valve that allows people to innovate, and it can be done in a very kind of like proprietary way. You mentioned before, there's a lot of RISC-V cores that are built into systems and you don't even hear about. And it's one of the things that analysts have problems with. Is like, how many RISC-V cores are being
no one knows.
Well, no one knows because people don't talk about it because they're innovating, and they're not going to go out and explain all of the innovations they did with RISC-V and kind of give away kind of their internal secrets, right? So there's much more going on than anybody really knows about.
So I think before we wrap up this podcast, I'd just like to ask you one more question, which is that if for the audience out there who are watching this episode, if they want to get involved with Bluespec Solutions, what would you recommend they do?
I recognize that they go to our website. If they want to look at some example cores that we provide, they can request to download a core. They can contact us directly with the contacts that are on the website. And just reach out, via email or through our kind of HubSpot form for asking for additional information.
Fantastic. I'd just like to say thank you ever so much from the Electropages team. It's been a pleasure having you on.
Okay. Thank you, Robin. It's good talking to you.